All right, welcome everyone to another iteration of the AQT Colloquium series. Today, we are joined by Ed Barnes. Professor Ed Barnes is a professor of physics and more faculty fellow at Virginia Tech, where he has been since 2015. Prior to that, he held a postdoctoral position at the University of Virginia and a senior research associate position in both the Joint Quantum Institute and the Condensed Matter Theory Center at the University of Maryland. He earned a doctoral degree in physics from the University of California, San Diego in 2006. And we're really excited to have you here, Ed. Please take it away.
Great. Thanks a lot for the invitation. Really looking forward to interesting discussions during the talk. Let me share my slides. You can see that okay, right?
Yes.
Yeah, so I wanted to talk about the way that control can enter into new types of quantum algorithms, as in particular simulation algorithms based on the variational principle. I'll say a bit about that. And then also how it can inform the way that we do dynamically corrected noise suppression. So, we're used to thinking about control. And by the way, please feel free to interrupt me with questions at any point during the talk. So we're used to thinking about the role of control in quantum information science as being, doing things like initialization and readout of qubits, or implementing quantum gates and circuits as needed for various algorithms. But I think an important point for this talk will be that there are many ways to realize a gate. We can use different waveforms, different control schemes to implement the same gate in many different ways. And an obvious question is which way is better compared to others. And we'll see, especially in the latter part of the talk, how we can use smart choices of control waveforms to combat noise while implementing some desired gate at the same time. And then the other aspect of the talk is this idea that, well, when we have quantum gates or some circuit that implements some algorithm of interest, at the end of the day, that combination of gates boils down to some particular control sequences which are applied to our qubits. And so an obvious question is, do we even need to talk about the gates in the first place? Is there a way where we can directly choose these control sequences to arrive at the final state that we want, or get at the information that we're trying to get at? So the first part of my talk will be about this control-based variational quantum simulation algorithm called control VQE, where we pursue this idea of eliminating the gates in favor of just directly controlling the pulses applied to the qubits. And then if there's time in the latter part of the talk, I'll talk about new methods for designing control waveforms to combat errors while at the same time implementing gate operations. So control VQE is an example of what's called a variational quantum algorithm. And the simplest such algorithm is called a quantum eigensolver, where the idea is you're trying to find the energy eigenvalues or eigenstates of some quantum system, for example, a molecule. So here, this is just a schematic of a two-atom molecule like hydrogen, for example. And the idea behind these algorithms, so they're hybrid algorithms in that they use both a quantum computer and a classical computer at the same time in tandem. And the basic idea is to offload as much of the computation from the quantum computer onto the classical hardware as possible to try to get at near-term things that we can do. So the less demand on the quantum computer, the more easily we can start to solve interesting problems of practical interest. And so the basic idea is that we need to first find a way to map our problem, like this molecule, onto the quantum computer so that the quantum computer can mimic the states of the molecule in some way. And then we want to be able to implement states of various sorts, parameterized by some variational parameters theta. And then through measurements and use of the classical computer, we figure out how to update those parameters iteratively until we arrive at what's hopefully a good approximation to the target state that we're trying to create on the quantum computer. So we're trying to create the quantum states corresponding to this molecule on the processor. And we keep doing this iterative process until we've minimized the energy, this expectation value of the Hamiltonian, as much as possible, following the usual variational principle from a first course in quantum mechanics. So a main consideration that comes into these variational algorithms is how do we parameterize the states or the circuits that we're implementing on the quantum processor? So there are two main approaches that people have been pursuing. at least outside of the work I'll talk about here. So one class of approaches is what we call physics-inspired. So try to come up with a quantum circuit that knows something about the type of Hamiltonian we're trying to simulate. So we can build it out of operators or gates which have a structure which is similar to things in the Hamiltonian, basically. So that's one approach. Another approach is to do something which is more hardware-inspired, meaning that given the fact that some particular hardware is more amenable to a certain type of C0 operation or other types of single qubit gates or so on, to try to build a circuit out of the gates which are more easily implemented on a given hardware. So both of these approaches have been applied in various groups to solve various types of problems variationally. And generally, these methods have a lot of shortcomings. They can lead to really long circuits, and they can also sometimes lead to issues known as barren plateaus or noise, where basically the algorithm gets stuck at some point when you're still very far away from the solution that you're trying to get to. And this is a consequence of using predefined circuits or predefined wave function ansatz, essentially. So what we really want to do is to be able to find circuits or ansatz wave functions which are capable of exactly reproducing the state that we're trying to find, while at the same time we're using as few gates as possible. And in our group at Virginia Tech, we've come up with two different types of algorithms to address this problem. And they have some connections between them, so I'll say a little bit about both. The first one that we came up with is called adapt VQE, and the second one is control VQE, which is the main focus of this talk. So first, let me say a few words about adapt, because some of the ideas here are going to be borrowed over into the control VQE algorithm that I'll talk about afterwards. The main idea behind adapt is that we do not start with a fixed circuit ansatz up front. Instead, we try to let the system that we're trying to simulate inform us about what the circuit should look like, step by step. So the idea is that we start with a pool of operators that we can insert into the circuit, but we only add one operator at a time. And every time we try to pick the operator that reduces the energy as much as possible. And every time we add that operator, and then we see, are we close to minimizing the energy or not? If not, we keep going. We then go and see which operator can we add next to most significantly reduce the energy. And we keep going until we reach some threshold. At some point, we'll see that the energy is no longer being reduced as we add more operators. And so we say that we've hopefully converged, and the state that's living on the quantum processor at that point is hopefully a good approximation to the state that we're trying to simulate. But because this is a variational algorithm, there's no way really to guarantee that you have a good approximation. All we can do is to test it in various cases for which we know the answer and see that it works well or not. But we can take this adapt idea, this idea of adaptively and dynamically growing the circuit step by step in a problem-tailored way, and compare that to other approaches like these physics-inspired approaches or the hardware-inspired ones. And what we find is that it finds the target state dramatically more quickly compared to these other approaches. So in this figure over here on the right, I'm showing these purple and brown lines, and the green line, they correspond to just doing basically fixed circuits, or circuits in which we've arranged the operators in a random way. And I've singled out one point here, which is this physics-inspired ansatz, which is which you would write down if you're using this approach for this particular molecule of beryllium hydride in this case. And you see that after a large number of parameters, a large circuit depth, essentially what that means, we still have a rather large energy error in the final state that we obtain. Whereas if we use one of our adaptive approach, like this blue and orange line here, we see that we quickly converge to the target state with really high accuracy using far fewer parameters, using a far shallower circuit. And so this adaptive idea seems to be quite powerful, and we've been doing lots of work at Virginia Tech, and other groups around the world have also been adding on to this to figure out what sorts of problems can benefit from this approach. So we've examined, for example, not just simulating molecules, but also doing optimization problems like QAOA, an adaptive version of QAOA, Gibbs state preparation, thermal state preparation, and various other ideas. And so far, it seems like it's a very powerful approach. But at the end of the day, it still is not yet enough to be able to do simulations of problems which are both of practical interest and things that we cannot do on a classical computer. So even though these ansatz are much more compact and much more efficiently generated compared to other approaches that people have come up with so far, the circuits are still not simple enough to be of practical use. And the main issue is that when we come up with a circuit using this or other approaches, every gate that appears in the circuit takes a certain amount of time. And at the end of the day, if we're not doing error correction, at least we're limited by coherence times and by imperfections in gates. And so all these things are really limiting the performance and preventing us from a practical type of advantage. But then this leads to the question, do we actually have to talk about gates at all? Thinking about the control side of things, can we basically acknowledge the fact that every gate is really some pulse being applied to the qubit, and can we forget about trying to implement C-naughts or Hadamards or other specific gates in favor of just designing control waveforms directly? And so can we avoid having to decompose some target unitary into this large sequence of gates, which can become very large if we're really restricting the types of gates that we're allowing ourselves to apply, like C-naughts and single qubit gates only. So this is what led us to think about this control VQE algorithm. So can we apply the variational principle directly to the device controls instead of using it to form a circuit based on gates? So the idea is similar to what we talked about previously for variational algorithms. So we still want to use a quantum computer together with a classical computer to systematically update the state living on the quantum processor in an iterative way until the energy is minimized as much as possible. But instead of building up a circuit on the quantum processor gate by gate, we're going to instead build up waveforms applied to the qubits in the processor step by step. So because this is a gate-based, because this is a gate-free approach, now we can no longer be agnostic of the hardware of the quantum device that we're using. To run simulations of control VQE either classically or quantumly, we have to say what kind of device are we talking about and how are the controls being implemented. So in the work that we focused on so far, we've mostly considered transmon qubits with a direct capacitive coupling. So here's just a schematic of 3 transmons. Here they have 3 different frequencies. In this schematic, I'm showing the same coupling between neighboring transmons and the same anharmonicity, but that doesn't have to be the case. In our simulations, we let these things vary. But given some hardware like this, some set of qubits, some connectivities, and also we have to introduce the way in which we're driving the qubits. So here I'm assuming analog controls and the rotating wave approximation just for concreteness. So we're applying a pulse, a single tone, in this case, to each qubit, and there's going to be some amplitude that describes the waveform and some frequency. And now the idea that we're going to borrow from adapt VQE is this idea of iteratively updating the state living on the quantum processor in a way that's informed by the problem Hamiltonian, the thing that we're trying to simulate. And as in adapt, we're going to add variational parameters, essentially one or a few at a time, until we reach convergence. So this is nice because we're only including as many variational parameters as we actually need to solve the problem at hand, instead of just upfront saying that we have 1,000 parameters and then we have to just optimize them all at once, which is not a very practical approach, as has been seen in numerous different ways. So the way that we can approach this adaptive version of control-based VQE is to, first of all, just suppose that we apply constant amplitude pulses to each of the qubits, as shown schematically here for 4 qubits. And initially, we optimize the amplitudes of each of these pulses and also the frequencies. But now the idea is that to introduce additional variability or flexibility in the pulses, we're going to randomly subdivide the time window into 2 parts. So for example, I can choose to cut all the pulses at this particular time here. And then I'm going to let the amplitudes on either side of the cut vary independently of each other. So then we rerun the optimizer, now with twice as many variational parameters as before. And we find, for example, something like this, where we have on each qubit some particular 2-part square pulse that's being applied in order to arrive at an approximation of the target state. And we can keep doing this as needed. So if, after doing this first cut, we find that we're not sufficiently converged in terms of the energy, then we can go and randomly pick another time at which to cut the pulses, introduce another set of variational parameters in those pulse amplitudes on either side of the cut, and optimize over them and find a new pulse or set of pulses for each qubit, which bring us even closer to the target state. And we can keep repeating this process of cutting the time window and introducing additional variational parameters as needed until we reach conversions. So we've tested this out through classical simulations of small molecules. So here's an example of the H2 molecule on the left, where I'm showing this dissociation curve. So the energy as a function of the bond distance between the two hydrogen atoms in the molecule. And so the blue squares here are what our algorithm produces, and the red curve is the exact solution, which you can easily solve on a classical computer. And you can see that at least on this scale, you don't see any difference between the two. And on the right, I'm showing the energy error for now 3 different molecules, lithium hydride, and hydrogen, and also helium plus, H plus. And this is the energy as a function of the number of time segments. So this is this process where I'm subdividing the time window and introducing variational parameters step by step. And you can see that even for the hardest problem, which is lithium hydride here, I only need 5 time segments in my pulses in order to reach a really good approximation to the ground state. So this pink region here is what's called the chemical accuracy, and it's basically what chemists tell us is the accuracy we need to be able to make sensible predictions for things like chemical reactions and so on. So we reach that regime even after only 3 divisions of the time window. And now what's really interesting is that if we take this algorithm, these results, and compare them to a gate-based approach, for example, this physics-inspired approach in the case of lithium hydride, there we find that if we do the gate-based approach, convert it into pulses and so on, that whole sequence takes 80,000 nanoseconds to implement to arrive at the ground state. Whereas doing this control VQE approach leaves us with pulses that only have a time span of 50 nanoseconds. So already for these really small problems, we're getting orders of magnitude reduction in the overall time it takes to generate the target state. And we have evidence that as you increase the system size, this discrepancy between gate-based and gate-free approaches grows pretty quickly. So I would expect that for a very large problem, which would be of practical interest, something that we cannot easily simulate classically, the amount of savings in terms of time could be really dramatic. But a challenge with this approach is that, it's even harder to simulate classically compared to the gate-based approach, because now we have to simulate the actual quantum dynamics of the hardware. So in this case, we're talking about a handful of transmons with couplings between them and pulses applied to each one. Simulating a system like that where we keep several levels for the transmons for good accuracy and so on is really expensive on a classical computer. And going beyond, I would say about a dozen qubits is challenging, at least for us, especially when you consider the fact that we have to do this optimization process of the pulses, which is time consuming. So compared to doing a gate-based approach, for a gate-based approach, you could simulate a few tens of qubits. But for control VQE, it's a much harder problem classically. So this problem is really begging for a real implementation on quantum hardware where you can get around this bottleneck immediately. Now, an interesting thing that happens, so in this algorithm, we fix the total duration of the pulse, and we optimize, and then we subdivide each of the pulses to introduce variational parameters and optimize those parameters, and so on until we get a good approximation to the target state. This total pulse time is a kind of like a meta parameter. It's something that we set up front. And an interesting thing is that as we reduce this total duration to smaller and smaller times, here you can see this is a 20 nanosecond pulse. Here I'm showing a 2-qubit case. So the pulse on qubit 1 is in red, the one on qubit 2 is in green. As I reduce the pulse time from 20 nanoseconds down to 16 nanoseconds, I see that the pulses start to assume a simpler and simpler structure, so that when I get down to this window here, Just something here. So when I get down to 15 nanoseconds, I see that the pulses start to assume a simple square shape. And if I try to squeeze the time even further below 15 nanoseconds for this example, we find that there's no solution, that I'm not able to converge to the ground state. So what this is showing is that there's a minimal time it takes to prepare some target state, given some initial state on the quantum processor. And there are some old math theorems that suggest that those time optimal pulse shapes should have a square form, which is exactly what we're seeing here. So what's interesting here is that we're actually reducing the time as much as conceivably possible, the time it takes to prepare the target state. So given some hardware, some collection of transmons with a certain type of drive and control applied to them, there is a minimal time it takes to prepare the target state, and this is what we're discovering in this problem. So this applies also to, yeah, please.
So this is a fundamental limit, right?
It's a fundamental limit, that's right.
Okay.
So it's a fundamental limit set by both the quantum hardware we're using and the problem that we're trying to simulate.
I see. And is there, so all of these different time lengths, are you, is this with the same accuracy for the final state, or?
Yeah, that's right. I'm using the same accuracy. So here things are converging well within the chemical accuracy regime. Yeah.
To the same amount, or just within the same regime?
To the same amount. It's 10 to the minus 5 or so.
Okay, I see.
Yeah, that's the energy error. Yeah.
This is quite interesting. Thank you.
Yeah, so there are lots of kind of high-level math theorems about this so-called minimal evolution time, or quantum speed limit, sometimes is called. But it's not so common that you see practical realizations of this. And so I think it's really interesting here. And this is a limit not just for control VQE, but this is a limit for any variational algorithm that's trying to prepare the ground state. It's going to run into this 15 nanosecond limit if you're trying to use transmons of this type of architecture. So because we're talking about transmons, we can also ask, well, what about the effect of higher levels? You know, we have the 0 and the 1 state, but there are other states which can be significantly involved in the evolution, depending on the way the control is applied and so on. And so here we considered what happens if we just add in the third level, at least initially. We'll just consider that first of all. And now if we calculate the success probability, meaning the probability that we arrive at the target state as a function of the total evolution time, what we find is that now the minimal evolution time, the minimal time it takes to reach the target state is reduced so in this example, the minimal time was about 20 nanoseconds if you only have 2 levels in your transmons, but now including the third level reduces that time down to around 10 nanoseconds by about a factor of 2 in this case. So this is unusual because normally we think about the presence of leakage states like this level 2 here as being problematic for algorithms, and generally you're trying to avoid leakage, especially if you're doing a gate-based approach. But here we're seeing that leakage is actually advantageous and that it's speeding up the time it takes, it's shortening the time it takes to arrive at the target state.
But this is intentionally including the third state, right?
Yeah. So
that is part of your quote computational basis here.
That's right. That's right. Well, I mean, I wouldn't call it, it's not part of the computational basis. So it's still the case that the target state only involves 0 and 1 for each transmon.
Interesting.
But I'm allowing population to leave the computational space and occupy the leakage states. And I'm not even demanding that all the population comes back to the computational space at the end of the evolution. I can have some population left outside of the computational space, but so long as the footprint of the state in the computational subspace coincides with the target state, that's good enough.
Thank you.
Yeah. So this is why leakage is not a problem and is actually a benefit for this variational algorithm, because any state which has the right form in the computational space, but perhaps has some population outside the computational space, any of those states is considered a solution to the problem. So by allowing leakage to happen, I, in essence, have increased the size of my solution space. And now instead of having one state being the solution to the problem, I have a large set of states which are all equally good solutions.
Can I ask a quick question about this?
Yeah, please.
So this is assuming that, okay, you have leakage, but you are also able to accurately classify it as leakage and not project it to some, like basically it doesn't get projected onto 0 or 1, but you actually read out and discriminate the leakage.
Yeah, that's correct. You need to be able to discriminate, identify that it's there. That's right.
I see. Thank you.
Yeah. So in addition to
So what would happen if you have leakage and then it decays back into the computational space?
So that would lead to errors in the final state that you have. Yeah.
Yeah. Fortunately, we can discriminate multiple states, so this will be fine. Please.
Yeah, and although I don't think I included the slide here, but as you go beyond 3 levels, we find that there's actually no further improvement in terms of the success probability as a function of time. So if you went to 4, 5, 6 levels in this picture here, the curves for 4, 5, and 6 levels basically coincide with the orange curve. So there's
is this for a particular problem, or is that generally true?
So we've checked it for a few different problems, and it seems to be a general trend. In this particular case, we're looking at the hydrogen 2 molecule at a particular bond distance. But I don't think we've seen cases where you get an additional benefit from the 4th or the 5th level in terms of total evolution time. But that could be a matter of the parameter regime and which problem you're talking about. There could exist some problems and some parameter regimes for the transmons where you would see a benefit at 4 levels, but we haven't seen that yet. So the fact that we've effectively increased the size of the solution space is one reason for the speed up. Another reason is that the additional Hilbert space also gives you a slightly shorter route from the initial state to the target state. And so it's really the combination of these 2 effects that leads to the overall speed up that we see. So this is what I plan to say about control VQE. Maybe I'll stop here in case there are any more questions about it.
Yeah,
I guess
I had another question. Okay,
Yeah.
go ahead.
No, go ahead. No.
Yes, my other question was going to be, okay, so you have to have a model, for example, of the transmon, and then you can sort of map out the ansatz pulses given that model, but how much do things like crosstalk and maybe, for example, non-local crosstalk, how much in practice and in experiment do you expect that to affect the ability to implement this scheme?
So I don't expect things like crosstalk or coherent errors to be very impactful because this is a variational approach. That means that effects like that can be corrected basically through changes in the pulse shapes. And I think that's expected to be true both for gate-based approach and this gate-free approach. But I think a possibly more important issue is if you have measurement errors, which would mean that you might be making not the right or not the optimal updates to your pulses, in which case you might be driving your system towards some other state away from your target state. So I would expect it to be robust against coherent errors and crosstalk and things like that, but maybe not as much against measurement errors, but that's something that we're still investigating. We're not sure exactly how robust it is to that.
All right, thank you.
Yeah, so that does make a lot of sense. I can see since you're basically just optimizing it with feedback based on where you're headed,
Yeah.
But so that makes sense. But how about you made some statements about how this technique scales. Could you repeat that? And is that, since there's a lot of discussion, a lot of not just theoretical frameworks, but theorems around what you're discussing. It seems like that is what informs a lot of this. How does this scale and with problem size and qubit counts and et cetera, et cetera?
Yeah, that's a very hard question to answer for any variational type algorithm. At the end of the day, it's really a heuristic algorithm. So this is true for any variational algorithm, actually, whether it's quantum or classical, that's still the case. And so how it scales, you can only really say by doing a bunch of examples and increasing the size and trying to pick out the trend. So for any VQE right now, there's no clear sense of the scaling, whether it's gate-based or gate-free. In this control VQE case here, it's even harder problem to answer what is the scaling, because we can only go to still rather small system sizes. But the examples that we've seen up to maybe 10 qubits or so is that we do get orders of magnitude improvement compared to fixed circuit approaches. So I would expect that trend to grow as you go to larger problems, because for larger problems, you have deeper circuits, and the more gates you have in your circuit, the more you're basically wasting time generating C-naughts and then doing more C-naughts to undo entanglement that you've created from your previous layer of C-naughts and so on. But it's really hard to make a definite statement about that.
Okay. Yeah, so that also makes sense. But the work that you've done so far that informs all of this is all simulation anyways, right? And so the exploration of the system sizes that you have explored so far, this has been simulation. So is that being held back, like your intuition on scaling and statements on scaling, is that being held back by like classical resources to do these simulations?
Yeah, definitely. I think, being restricted to system sizes of 10 transmons or less is very restrictive. I think if we can double that or triple that or whatnot, that would give us a lot more information about the scaling for sure.
So HPC could come in handy just to give you a sense of how this goes.
Yeah, possibly. Yeah.
Okay. I'm sure Katie's taking notes there. Sounds good. All right. So I guess, one last question. Since you are really taking into account the individual qubit and coupling layers, and you're going with fixed frequency transmon and coupling, it seems like, and I can see why you would make that choice considering where you would want to run this. But if you had kind of your pick of qubit implementation and coupling, have you given thought and have you done simulations on what would be the most amenable to enable best performance for this type of approach?
Yeah, we've done a little bit. So we've so far we've focused almost entirely on transmon systems, but we've explored different connectivities, whether it's a linear array or all-to-all connectivity, that kind of thing. It does seem like the more connectivity you have, the faster you can reach the target state. But that's, again, still based on small systems of, say, 4 transmons.
I guess it would matter only if you're approaching your coherence limit. And all of the examples you're showing, tens of nanoseconds, like these don't really, at this level, it wouldn't really make a system. I guess part of my question is, what is the longest quantum experiment time that you have simulated so far? Is that really running up against coherence times?
Actually, nothing we've done so far runs even close to coherence times. Yeah.
Wow. Okay.
Yeah.
Can I ask questions? So you simulated the circuits. Have you tried to run on a real hardware? Because then you don't have this 10 qubit limit.
Yeah, that's right. So we have been trying a little bit with IBM hardware. I have a student that's been trying to use the pulse scheduler in IBM to implement arbitrary waveforms, essentially. It's been really slow progress because it's been really hard to figure out all the calibration stuff and settings in IBM. It's not a very user-friendly system as far as we can tell. So he's made a lot of progress in doing a simple simulation of the H2 molecule, but it's still not, I think it's sort of at the edge of chemical accuracy, and we're still trying to pin down residual errors and things like that to get beyond that threshold. But it's a really slow process.
So do I understand correctly, you are trying to get a Hamiltonian model for the qubits from IBM based on their calibration? This is the issue?
Well, so that you can download the Hamiltonians for the transmons from IBM. Supposedly they're precise, but then when we run certain pulse waveforms and look at the tomography for them, they're not exactly what they're supposed to be. And it's been a lot of just trying to pin down exactly where the deviations are coming from. So we're not quite sure exactly where the issue is. Yeah, I think if I had a better understanding, we would have solved the problem by now.
Is there another question? Sorry.
Go ahead.
Hey Ed, I love the talk so far. So sort of following up on that last part about the model that you expect with the qubits. So this method is dependent on the model, and let's say there is some deviation from a known model. Basically, you won't be able to use the same method, or is that not the case?
So our simulations, our classical simulations depend on a model. That's true. But ideally, this would be run on hardware, and the updates to the control pulses would be determined directly from measurements on the hardware, in which case there is no need for a model at that point.
Right.
Yeah.
Okay. So it actually does not depend on there. So, but the parameter space of that can be quite big. I guess I was just looking at the pulses. They seem like there's quite a few, say, wiggles in there, and you can think of those as independent parameters there. And if you're optimizing over that space, that seems like, I guess my concerns about scaling there.
Yeah, so I should clarify. So let me go back a slide here. So for these simulations of, say, lithium hydride, which is the red curve here, here we're just starting with a constant pulse on every qubit. And then we do this process where we randomly pick a time and then divide the pulse into two parts and introduce one more variational parameter per qubit and do that iteratively. Here we reach chemical accuracy with only 3 parts to each pulse. So it's just a 3-part composite square pulse applied to each qubit.
I see. Okay.
In this other study here, when we were trying to explore this minimal time, this minimal evolution time, there we knew that at least we expected that we would see these bang bang pulses emerge if you allow basically arbitrary waveforms. So we just wanted to show that that actually was the case. So here we took a large number, maybe 1,000 time steps, allowed each time step to have a different amplitude, and then we wanted to see that as we reduce the overall evolution time, it converges to a square waveform. But this is not to say that you actually have to have 1,000 parameters per pulse to run the algorithm.
I see. Okay, thank you.
I guess one last question from me, at least. Do you have any intuition about? So it looks like basically because you have this freedom to send whatever pulse you want to send, you're always coming back down to like 10-20 nanosecond entire experiments for the quantum part of it.
Mm-hmm.
Do you have any intuition whether, like, how big of a system size would you need to have for this to even start to approach, microsecond scales and tens of microsecond scales for decoherence to become a problem?
Yeah, that's an excellent question. I'd really like to know the answer to that. But I think without being able to run it on hardware, it's really hard to answer.
This is quite fascinating. Okay.
Sorry, can I ask one more question? I know this has become a drawn-out question session. I'm just curious about something else. So when I look at these pulse shapes, they obviously have a lot of, I would say, like jagged features on a rather short time scale. And like in principle, when we actually generate schedules of pulses and upload them, we have many things that are sort of like factors in the actual pulse the qubit will see, such as filtering, and like the sampling time of your AWG. There's many factors. How much do you expect? Like, for example, it seems like you were trying to do this extremely fast with many features and say 50 nanoseconds, but these features, a lot of them in practice will probably be smoothed out by both the basically just like the sampling rate and especially the filtering in the fridge. Do you think that might limit how fast this can actually be done in practice?
So at the moment, I don't think so. So I should reiterate that, I would not recommend trying to implement, say, the green pulse shown here. That's totally not necessary, because if you look at these examples, right, the pulses that generated this red curve at this point only have 3 parts. So we're talking about something like this, where we have a simple square waveform where it transitions to a different amplitude twice. And I would expect that if you impose some rise time limits or some bandwidth constraints, then this would become just a smoothened step where the rise time could be a nanosecond, within typical AWG limitations. And I would expect very similar performance.
Got it, thanks.
Yeah.
So I guess kind of the point of the three plots you were showing converging to a square wave, that was just to show this conforms with the theorems that had predicted.
That's right. So this is to show that even if your pulses have 1,000 parameters and can assume various shapes, as you restrict the overall time, those shapes become really simple square pulses. So to
Which
make
I believe, yeah.
So
Yeah.
to make the
For us,
demonstration,
it's a positive. Yeah.
Yeah. So this is kind of showing that even if you have 1,000 parameters, you don't need them because the actual time optimal solution is a simple square waveform.
Yeah, it's quite encouraging.
Yeah,
right.
I agree.
Thank you. Any other questions for this? This was all of the control VQE part of the talk, right? The rest of it is going to be a bit different.
Yeah, and I don't know. I mean, depending on the time, we don't necessarily have to.
No, we have time, and at least I have definitely a lot of interest. But I just want to see if there is any other questions. If anybody else has any questions about this part of the talk, please ask now. All right, so then let's keep going to the next part.
Yeah, so the next part is about dynamical noise suppression, and I'll just try to give you the overall sense of what this research is about. So I'm not going to go through all of it, I don't think, in the interest of time. But the basic idea here is that we have.
If I may interrupt, I would say that just so for your information, I think this is a topic that will interest a bunch of people.
Okay. Yeah, and as before, please feel free to jump in with questions as I go along. So the question here is, how do we design pulse waveforms that can implement target operations while at the same time suppressing noise effects? And so this is an old idea that dates back to things like Hans-Bin echo, where if you apply a pi pulse around the right axis halfway through the evolution, you can basically reverse the effects of dephasing. And this sort of idea has been applied quite heavily in quantum computing already. So there are generalizations of Hans-Bin echo where instead of having a single instantaneous pulse halfway through the evolution, you can apply multiple pulses at various times. And then depending on what kind of noise you have, choosing the times appropriately can dramatically improve the overall coherence time. So this has been shown in lots of different qubit type experiments. I think all the examples here are spin qubits, but other platforms have benefited from this sort of technique as well. And generally, the more pulses you apply, the longer and longer the coherence can become until you reach some limit at which other effects start to dominate beyond this dephasing type noise. So those techniques like Hans-Bin echo and its multi-pulse generalizations, they are basically designed to keep the qubit alive, have it come back to the same state as over and over again for as long as possible. But in reality, we want to be performing operations on the qubits while noise is afflicting them. So then the question becomes, how do we do a similar idea, but while we're implementing some non-trivial operation on the qubits? And so by non-trivial operation, I mean, we're trying to design the evolution. So here's just the Schrodinger equation for a single qubit. We have some Hamiltonian like this with a detuning parameter, say on the diagonals here, and some envelope omega of t on the off diagonal. And the goal is to choose omega of t in such a way that you arrive at some target final evolution operator, which is your gate. So for example, if you set the detuning to 0 and choose the area of omega of t to be pi, you can realize a NOT gate. So what if we have noise afflicting the qubit while we're doing this gate? So imagine we have fluctuations in the detuning parameter and possibly fluctuations in the control field itself. Can we find smart choices of omega of t such that these effects epsilon and delta omega are eliminated as much as possible from the final target evolution, so that the actual evolution that's realized is this target gate that we want, and the deviations caused by the noise are suppressed. So here I've assumed they've been suppressed at first order, but perhaps you can cancel second order effects as well. And so the question is, how do we choose this pulse such that these higher order effects or the first order effect is canceled. So this is essentially what spin echo and things like CPMG are doing in the case where you're just trying to implement an identity gate. And if you try to generalize this to pulses which are not delta functions, not instantaneous, things get much more challenging. So initially, I looked at this problem a long time ago as a postdoc, along with some colleagues of mine. And we were posed this question by some people working on spin qubits, actually. They asked, so there are all these control schemes from NMR where you can apply square pulses of finite amplitude in the right way and cancel things like detuning noise and other effects. An issue with the spin qubit platform that our collaborator was looking at is that they were not able to make the pulses both positive and negative during the evolution. These were exchange pulses on singlet triplet qubits, which basically means that the pulse amplitude is always non-negative. And so a lot of the NMR literature goes immediately out the window as soon as you impose that constraint. And so we worked on this problem to try to generalize NMR type ideas to this constrained spin qubit problem. And we came up with pulses like this example, which cancel both detuning noise and control field noise at the same time. And the nice thing about squares and also delta functions is that mathematically you can solve everything analytically. It's pretty straightforward. But the issue that we ran into is that I then went to Harvard for a month and worked with our experimental friend to try to implement this sequence. And it turned out to be really challenging because of finite rise time effects and other things that deform these perfect square shapes into something which doesn't quite look like this. And so the basic takeaway message for me from that experience was, can we get away from squares and delta functions and do smooth pulses that respect bandwidth constraints and other things, while at the same time implementing noise-resistant gates? So I basically went back to the drawing board and just wrote down the simplest possible problem where you have, say, zero detuning, but there could be noise in the energy splitting because of the environment. And the question is, how do you choose omega of t such that this noise is canceled, at least to first order? And so you can expand out the evolution operator and the perturbation series and the noise parameter and derive some conditions that have to be satisfied such that that noise is canceled. And so these are the conditions you would solve to derive Hahn spin echo or CPMG or other dynamical decoupling sequences. But the thing that we noticed is that if you focus on the first order term in this expansion, it has some coefficient which we call G1 of t. This is a complex function because it's a solution of the Schrödinger equation. And so you can plot it in a complex plane. So here's G1 of t as time goes on. So you start off at 0 because initially there is no error. And then as time progresses, it traces out some path. And we can call this the error curve because it's basically giving us a measure of that first order error in the evolution caused by the noise. Now, what's interesting is that if you stop at some time t and look at the second order derivative of this curve that we're drawing, it turns out to be 1 over the pulse amplitude. And another interesting thing that you can show from the math is that the length of this path that we're drawing is actually exactly the evolution time. So those sounds like simple statements, but it's actually a really powerful observation because if you think about what we're trying to do, we want this path to come back to the origin at the final time. Because if it comes back to the origin, that means that the first order error is canceling. And the question that we're trying to answer is what pulse omega of t implements a trajectory like that? And we actually have a reverse engineering way to answer that question because we can draw any closed path, anything that comes back to the origin. We're guaranteed that the noise is canceled. And we can read off the pulse that does that by computing the curvature at every point along the path. So this is doing dynamical decoupling, but with a smooth pulse. If the curve that we draw is smooth, then the pulse itself will be smooth. And it's actually a general solution to the problem. We've made no assumptions. So any closed curve that we draw on the plane will give us a pulse that cancels noise. And so we can start drawing closed curves. So 19th century mathematicians had favorite lemniscates, which is just a word that means figure eight. So there was a mathematician named Gerono who had this favorite lemniscate. There's a formula, but it doesn't matter. Bernoulli had his own favorite figure eight shape. And so one way you can generate nice simple formulas for smooth closed curves like this is just take those figure eights and chop them in half. And a third important fact that we found is that if you make the curve close in such a way that there's a cusp at the origin, then the opening angle of this cusp tells you what rotation you're implementing on the qubit. So if I look at this Hamiltonian that I'm considering here, I can see in the absence of the noise, when epsilon is 0, I'm implementing x rotations. And so this opening angle at the origin is telling me what the angle of rotation is about the x-axis, up to an additive factor of pi, but that's a detail. So then the statement is that if I want to generate a particular x rotation that cancels noise to first order, I need to draw a closed curve with the right opening angle at the origin. And once I draw the curve, I'm guaranteed that the noise is canceled. And I can read off the pulse that does it by just computing the curvature at each point. And in this case, this is what the pulse looks like. And if I want to generate different x rotations, all of them robust, then I just need to draw different closed curves with different opening angles at the origin. Here are 4 different such curves, different opening angles. Each of these generates some robust x rotation, and you can see the pulse for each of these cases over here. So a nice thing about this finding is that it's a general solution to the problem. I can find any pulse that cancels noise just by drawing closed curves. As I draw the curve, I know 2 things immediately. I know exactly what the pulse looks like because the pulse is just the amount of bend in the curve as they go around. And so if I want a nice smooth pulse, I just have to draw a nice smooth curve. It doesn't bend too much. And I know exactly how long it takes the pulse to do the gate because that's just the length of the curve I'm drawing. So here, for example, for this orange curve, I can see this is the most bendy curve. It has these 2 points like here and here where it bends the most, and you can see that translates to a peak in the pulse amplitude. So if I don't like that, then I have to avoid drawing curves like this. So this is a general solution to the problem, which means that I should be able to go back and understand all those famous dynamical decoupling results like spin echo and CPMG and so on in this geometric language. So spin echo, for example, looks like this. So spin echo is just an instantaneous pulse halfway through the evolution. That means for the first half of the evolution, there is no pulse. The pulse amplitude is 0, which means that the curvature is 0. And that means that I'm drawing a straight line. So I start here at the origin, I draw a straight line, and then halfway through the evolution, a delta function pulse is being applied, which means that the curvature is infinite. So I turn around infinitely fast at this point. And then after that, again, there is no pulse. So I'm just retracing the same line all the way back down to the origin. And since I'm stopping at the origin at the end, the net effect from the noise is canceled at first order. And all the other famous dynamical decoupling sequences based on delta function pulses are similar. For example, in CPMG, here the origin's in the middle of the frame now. I start here, I go up, and then there's a delta function pulse, which means I turn around, I go back down. For CPMG, you wait twice as long before the next pulse comes, and that corresponds to going all the way down here. And then the next pulse comes, and I turn around again, and I come back to the middle. So two pulse CPMG would then stop, but you can keep going back and forth up and down this line segment as many times as you want and keep adding pulses to your CPMG sequence. So you can understand all the famous dynamical decoupling sequences in this language. It just corresponds to going up and down the line some number of times. Every time there's a pulse, you turn around. You can also derive infinitely many more sequences that people haven't talked about so far, just by changing when you turn around. So long as you stop at the origin at the end, you're canceling the noise. But the general solution for arbitrary waveforms is to draw curves in a plane. And this is what you want to do if you want to have pulses which have finite amplitude. So this is the main idea behind this line of work. So maybe I'll just pause for a second in case there are any questions. And then I'll just try to highlight some of the things we've done with this idea. Okay, so you can ask things like, well, what happens if I want to cancel higher orders of the noise? It turns out that now canceling the second order corresponds to making sure that the curve you draw has a zero area. So if I draw a figure 8 like this, then in the upper half plane, I'm going counterclockwise, and the lower half plane, I go clockwise. And so there's a relative sign between the areas of the top and the bottom lobes. And so the net area is 0. So here are 4 different figure 8-like curves, and they all correspond to pulses that cancel noise in the detuning to second order. But all of these figure 8s have the same opening angle at the origin, so they all actually implement identity gates. If I want to implement a non-trivial X rotation while I'm canceling noise to second order, then I have to draw less symmetric curves like the ones shown down here. And by introducing a different opening angle at the origin, I can generate different types of X rotations. And so long as the net area enclosed is 0, then I'm canceling noise to second order. So another nice thing about this is that you can, since the length of the curve is the evolution time, then by drawing shorter and shorter curves, I'm getting faster and faster pulses that implement the same gate. If I don't put any constraints on the pulse, then I'm just going to end up drawing infinitely small curves, which will correspond to infinite curvature, which in turn means I'm talking about delta functions again. If I want to avoid those unphysical situations, then I can impose a bound on the amplitude, which means I'm imposing a bound on the curvature. And then you can ask, what is the shortest curve that satisfies some bound on the curvature that implements the gate I want to implement? And you can solve that systematically. We've done that. It turns out that the time optimal pulse for any X rotation corresponds to a 3-part square pulse. But then, I started this by saying I don't like square pulses. You can then take this absolute time optimal solution and impose bandwidth constraints on your pulses to get as close as possible to this global time optimal solution. We've generalized this in various ways, so you can consider a non-zero detuning now, moving away from the simplest possible problem. It's very much the same story, the main difference being that now you're drawing curves in 3 dimensions, but so long as the curve is closed, you're still canceling the detuning noise to first order. And there's a straightforward generalization of the second order cancellation condition as well, which is that when you draw your curve in 3 dimensions, you have to make sure that 3 orthogonal shadows have 0 areas. This is again the totally general solution. Any pulse that cancels noise to second order has to correspond to a curve with these properties. This formalism we've also extended to other types of noise. So trying to cancel both detuning noise and control field noise at the same time. You're still drawing closed space curves, but now they have to satisfy a few different conditions on top of that, which we've worked out in detail in full generality. And we've also found systematic ways to solve these constraints on the space curves to generate new pulses that cancel all kinds of noise. And this idea generalizes to an arbitrary number of qubits. For any number of qubits, the evolution of that system is described by some space curve in some number of dimensions. And canceling noise means that you have to make sure that the space curve satisfies certain properties. And then you can figure out what the control fields are by looking at generalizations of the curvature for these higher dimensional space curves. So we worked out examples of doing 2-qubit entangling gates this way, or doing a 1-qubit gate in the presence of crosstalk with a 2nd qubit, and various other things. So here's just a short list of some things that we've applied this to. So for example, we've applied it to Landau-Zener type physics, where you're trying to drive your system through an avoided crossing, despite the fact that there might be noise causing the avoided crossing energy gap to fluctuate in time. You can adjust your sweeping waveform in such a way that you account for that, you correct against it. And we've also, for example, extended this to time-dependent noise. So the examples I talked about so far, I was assuming that there's this noise parameter epsilon, which is an unknown but constant parameter constant throughout the evolution of a single pulse. But I can extend this to account for the fact that epsilon can change during the pulse. And so if you're interested in this stuff, there's a review article that we wrote last year. You can take a look at, has most of it. And with that, I'll just show my summary. So for the latter part of the talk, the main takeaway is that any robust gate corresponds to a closed curve. And by designing closed curves, you can design robust pulses. And geometry gives a nice global view of the optimal control space. So I view this as complementary to things like grape or other numerical recipes for designing waveforms where, typically you're getting some local optimal solution that's dependent on the initial conditions you feed into the optimizer. Here we're getting a global perspective on the solution space. We can find the time optimal solution given pulse constraints and given some target operation that we want to implement. And then we can work from that. And then I also talked about gate-free algorithms in the first part of the talk, ways to speed up dramatically the time it takes to prepare target states for quantum simulation on a quantum processor without using gates. So with that, I'll answer any other questions, and yeah, thanks.
Thanks so much, Ed. That was a fantastic talk.
Thanks.
So we are already at the end of the hour. So I know that some folks have other obligations. The experimental side of these will deserve a lot of deep questions, and I'm definitely interested, and I know that a bunch of folks here would be interested as well. But for now, are there any? So I think it might be worth it to have a follow-up meeting to discuss more.
Yeah, that sounds good. That sounds good.
But are there any quick questions here from folks? Okay, let's Monica, could we stop the recording here?